Many students struggle with sequence problems, not because the algebra is difficult, but because they start calculating before they have identified the problem type. In an exam setting, your first priority is matching the question to the correct mathematical tool. Think of this as a diagnostic phase that happens before you ever pick up a calculator. To do this reliably, we use a four-step framework: spot the pattern, choose the formula, substitute carefully, and check the answer. Mastering this sequence allows you to look at any unlabeled number pattern and determine the exact path to the solution. This structured approach removes the need for guessing, ensuring that you apply the correct logic to earn every available mark. Step 1 is to spot the pattern. Identify what stays constant between terms. In the sequence 6, 11, 18, 27, the first differences are 5, 7, and 9. Since these vary, we look deeper. The second difference is a constant positive 2, identifying this as a quadratic pattern. This reveals the rule. Constant first difference is arithmetic. Constant ratio is geometric. Constant second difference is quadratic. Identifying this mathematical signature is the only way to ensure the formula you choose in the next step will actually work. Step 2 is to choose the formula. You must distinguish between Tn, which finds a specific term, and Sn, which calculates the sum of a set of terms. A frequent error is using a sum formula when the question only asks for the value of a single position in the sequence. Always verify if the goal is a total or an individual value. Sigma is a shortcut for a sum. The top is the upper bound, the bottom is the lower bound. To count terms, subtract the lower bound from the upper, then add 1. So 8 minus 3 plus 1 equals 6. Once you can translate sigma notation into these basic components, you can select the correct summation formula immediately. Step 3 is to substitute carefully. For a geometric sequence with T2 as 12 and T4 as 3, we divide the equations. The a variables cancel, leaving r squared equals 1/4. Taking the square root, we find our common ratio is 1/2. If we are asked for a sum to infinity, we cannot simply start calculating. We must first check if the series converges. A sum to infinity only exists if the ratio is between -1 and 1. On the left, a ratio less than 1 settles at a fixed value. On the right, a ratio of 1 or more grows indefinitely. Our ratio of 1/2 passes this test. By substituting our first term of 24 and our ratio into the infinite sum formula, we get a result of 48. The formula will still produce a number even if the ratio is too large, but without verifying convergence, that output is mathematically meaningless. Finally, we reach step 4, check the answer. This is a logic-based review of your result against the constraints of the pattern. If an increasing sequence starts positive and grows by 4, the sum of 20 terms must be a large positive value. Calculating 860 for these conditions passes our logic check, whereas a negative or tiny decimal would signal a calculation error. If your result had been negative or a very small decimal, it would indicate a mistake during the substitution or simplification phase in step 3. This final logical evaluation ensures that your mathematical output truly aligns with the observable behavior of the mathematical sequence. This diagnostic framework is most effective when applied to word problems, where the pattern is not immediately obvious. Consider a tank that loses 20% of its water every day. We need to find the total amount of water lost if this process continues indefinitely. We map the information to our steps. A percentage loss indicates a geometric ratio of 0.8. The word indefinitely indicates we need a sum to infinity. To practice this, download the linked worksheet and go to the Mixed Practice section. Apply these 4 steps to the first problem you see. Navigating complex mathematics requires the ability to recognize and decode the structure of the question before you begin the work of calculation.